So, of course, I want to start by saying thank you, everyone, for joining. My name is Cody Armstrong, and today we're talking about advanced assembly motion in Onshape. So, we're really going to focus on what it takes to create some of these more advanced movements that you'd like to see in your assemblies in Onshape. Now, as I always say with these webinars, we really encourage you to ask any questions that you'd like. There's a questions dialog in the GoToWebinar control panel. Feel free to ask any question, and I'll do my best to stop and address the questions as we go through today's webinar. We have a lot of different things to get to. I want to go through as many of the various movement types that you may want to create in Onshape. So we've gotten a lot of questions about how do I create this type of motion or that type of motion in Onshape. And what I was hoping to do is put together a webinar that kind of focuses on all those frequently asked questions and all those movements that users are trying to get. So let's dig into it now. The agenda today is pretty straightforward. We're going to start really simple and introduce you to the concept of mates and relations just to have a base level set. But then we're going to get into examples, and I have a few simple examples just to kind of cover the core mechanics of how these different mates and relations work. But then we're going to get into some of the more complex assembly motion, the combinations that can give you, realistic movement in designs using, tangent mates or, gear relations, whatever the example may be, or even combinations of these. As I always say with these webinars, really encourage you to ask any questions that you'd like. There's a questions dialog in the GoToWebinar control panel. Feel free to ask any question, and I'll do my best to stop and answer them. All right, so let's get into it. Now, we're going to start really basic, and as I mentioned before, we're going to start with just a brief explanation of mates and relations. And mates are, of course, the way that we constrain parts relative to each other in the assembly. So to put it in a single sentence, what is a mate? It's a way to constrain a part relative to other parts in your assembly. Now, the way Onshape handles mates is a bit different than many other CAD systems. If you have experience with past CAD systems, we use mate connectors to define the relationship between parts. So rather than using a combination of faces, for instance, to define a single part's location, we use one mate connector on each part. And it greatly simplifies the approach. It also makes it very easy to do things like animate, which we're going to cover here later. But the big thing is just keep in mind, think of those mate connectors and those mate connection points as the points where two parts meet. And what we do is we define the movement between the two parts based on the type of, mate connector that you have and mate that you choose, right? So if I choose a fasten mate, for instance, I'm fastening all degrees of freedom. It can't move at all. If I want, rotary motion or rotation, I would choose something like a revolute mate. So the type of mate that you choose defines how much motion there is between the two things you're mating. So that's a key thing. And as you're getting started, what I'd recommend is choose different mate types. You can choose a different mate, hit the animate button, and it will animate the degrees of freedom. And it'll give you an idea of what each of the mates do, and it's a quick way to learn them. So that's a simple intro into mates. If you haven't gotten into assemblies in Onshape yet, I definitely recommend checking out past webinars we've done, assembly basics. If you do a search, especially on our YouTube channel, we have a playlist of past webinars, but definitely check out one of, kind of the essentials assemblies webinars that cover mates in greater detail. Now, mates are important only to understand the next step. And this is really when we start talking about the motion part of Onshape, right? When we start talking about how do we get realistic motion in our assemblies, well, there's a few important relations that can help with that. So what is a relation? Well, it uses existing mates to define movement between parts. So it uses the mates that you defined to, between your parts, and it uses that to define a relative motion. Now, I'll show you what that means in just a moment, but it brings up an important caveat. A relation must use existing mates, right? So you must have already mated the part into place, and then you use that mate to define what your relation would be. Now, it constrains the degrees of freedom that you have in your mates. So in the top left corner, I have a rack pinion example. You can see as I'm rotating it up and down, you can see that rack pinion driving up and down, just like you would in a real arbor press. Well, that's the linear degree of freedom of a slider mate, right? And the rotational degree of freedom for the handle. So what we're doing in a relation is we're constraining those degrees of freedom. Now, there's 4 basic types of relations: gear, screw, rack pinion, and linear. Now, these aren't the only commands that will give you motion in the assembly, but they are 4 of the biggest. So again, gear, screw, rack pinion, and linear. Now, that's a simple explanation of a relationship, but where are the practical applications for this? Where would I actually use this? And the first example, of course, is gears. Any kind of gear movement that you need in your assembly, you would use a gear relation for. Now, I'm showing an example of simple spur gears, but it could be worm gears, could be bevel gears. All of those really fall into the same gear relation, same command. So a gear relation is very simple. You have 2 revolute mates or 2 rotational degrees of freedom in your gears, right, that allows them to spin. You simply define a ratio between those 2 mates. I mentioned before, relations require that you have mates already established. And what we're doing with a relation is we're defining a ratio between that, the movement between them. So we're choosing 2 mates, they should say, with a rotational degree of freedom, right? In many cases, that would be something like a revolute mate. So enough slides. Let's get into an example of this. So this is one of those simple examples that I mentioned earlier. I want to start really basic, and this is a good example of that. I just have a simple, plate with 2 gears mounted to it. Now, 2 things I want to point out before I start the gear relation. Notice each mate, right? Revolute 1, revolute 2. These are the mates that have attached the gear to the base, right? So you'll see revolute 1, revolute 2, just edited here, you'll see the 2 mates defined. It's very easy for me to define a ratio between them. But again, these mates had to have existed beforehand. So that's the key thing I would say, is just make sure in any of the relation examples that I'm going to give you, you have that existing mate in place, right? And then it's really easy for me just to simply define a ratio between them. Now remember, you're defining a ratio of the first to the second. So in this case, for every 1 rotation, I get 1.25 rotations of that second mate, right? So that's a very simple example. Of course, the key thing there is it gives you that ability to set a ratio between your different gears in this example. Now, I do have another thing I wanted to point out here, and that is just an aside. If you're doing a lot of gears, bear with me for just 1 second here. If you're doing a lot of gear type work, one important tip that I'd recommend is using either rotating a mate connector or rotating the actual mate itself so that you can get the gears aligned. That's probably one of the more common questions I hear. How do I align the different gears in an example like this? And it's fairly straightforward. You can right-click and edit the mate connectors associated with them, and you can rotate as much as you'd like. Right? So I can rotate this part around, and it will shift, and it will line up those gears. So just a quick tip. If you're looking for a way to align gears in this type of an example, rotating that mate connector by editing it here will allow you to get that alignment. Right? And then when you go to apply your gear relation, you have it. But that's a simple example of the gear relation. Again, all we're doing is defining, here's the 2 revolute mates that attached my gears, so to speak, right? And what I want to do is, of course, I want to define a ratio between them. Right? Question. I joined late and I missed it, but can a gear ratio be entered as an actual ratio? No, not in the way the example. Think of it as a ratio of first to second in your selections. So that's the way I'd consider it. It's not you're not entering an actual gear ratio. It's just the ratio of rotation relative to the first and second selections. All right, so moving on. That's a simple example of a gear, right? Just simple rotation. But when we get into something a little bit more complex, just keep in mind it's really this same tool. So here's an example of a worm gear assembly. And in this worm gear assembly, you really have the same goal, right? For every X amount of rotation of this, I expect X amount of rotation here. So again, the math, the formula is very straightforward. You find the 2 rotational degrees of freedom. Remember, in this case, just like the last case, it's a revolute mate, but any rotational degree of freedom will work. And I define a ratio between them, right? Gear relation, I choose my two ratios right here and here. Then I say, I want 30 to 1, right? So first relative to the second. Now if we do a quick animate here, let's see if I did this right. There we go. So for every 30 rotations here, I get one full rotation here. My point in this is, it's still a gear relation, whether it's worm gears, spur gears, bevel gears, any of those applications is still just the same command. And you're really just still doing the same thing. You're setting that rotation ratio. For every 30 rotations here, I get one here, or, depending again on the order that I chose. Now, one quick tip that I have, I didn't mention it, but it's going to be helpful for me throughout this webinar, is animating a mate. And one of the neat things about our approach to mates is it makes it very easy to animate a degree of freedom if you have it. So, for example, to show you that motion, rather than grabbing and dragging and spinning, which you can certainly do, it's just so much easier to right-click a mate and say animate. So any mate with a degree of freedom, with any kind of movement, will have this animate option in the right-click menu, and all you got to do is hit play, and it will animate the motion of that mate, right? In this case, it's just a revolute mate, so it's spinning that revolute mate, but that, of course, gives me that realistic worm gear rotation that I wanted to check, right? So just another tip, any mate with any degree of freedom, you can just right-click and animate, right? All right, so that is another example of a gear relation, again, right here in the toolbar, whether you're using spur gears or worm gears or bevel gears, any of those, they really all fall under this one gear relation command. Question, are there chain, sprocket, belt, pulley tools in Onshape? Well, we do have a specific belt command. It's a feature script feature that you can use. It's not in the standard toolbar, but you can add it to your toolbar. I think the short answer to your question is no. We can use the gear relation, to accomplish the same thing, a ratio between sprockets, for instance, but you're not going to model the chain, right? That's something not very common in just about anywhere. Belts is another scenario, and we do actually have a feature script feature for belts. So if you're interested in belts in particular, in your Part Studio, in any Part Studio, you can add it to your toolbar. You'll see a plus icon in the far right corner, and I believe the feature script belt feature is there. So I'm going to go all the way to the right here and add a custom feature. And if I go to feature script samples, there is a belt feature right here. And that will generate a belt for you based on a number of different pulleys. But you're not really animating, the movement of the belt. It's more just figuring out what the length of the belt is and those types of things. So there is a feature script belt feature. I'd recommend if you do that a lot. If I were just doing, a ratio of sprockets, I could easily just do a gear relation, and there's no chain type of feature. All right, so moving on, that is a few different examples of a gear relation. And again, they work in any of those applications that we were talking about. What I'd like to get into next, one more. This is just a cool example. Bear with me here. So gear relations, you can really take them to the nth level, so to speak, right? Let's animate something like a planetary gear set, and you get that realistic gear motion. So remember, this is just a combination of gear relations, creating that kind of planetary movement, but definitely a neat example, and really just a combination you can see here of 3 different gear relations, right? All right, so moving on, the next example that I wanted to talk about, we've discussed worm gears, again, same thing, using a gear relation. So the next thing I wanted to discuss is a rack pinion relation, and any type of rack pinion scenario that you wanted to get realistic motion. And the key difference here is, for every rotation, I would expect a linear travel, right? And that's a bit different than a gear in that we're just defining 2 rotational degrees of freedom. So a rack pinion, as I rotate something, I'd expect it to move in and out, up, down, whatever the direction is, but linear. And what you're essentially doing is saying for every 1 rotation of this, I expect X amount of travel in this part, right? So we're choosing mates with 1 rotational degree of freedom, 1 linear degree of freedom, right? Those are the key things we're going to define. Here's the rotation of the handle, and here's the up-down movement that I need. right? All right, so let's get into a simple example of this, and I wanted to show an arbor press, so bear with me. But fairly straightforward, very similar to the gear relation in that you're just saying, here's the two mates, and here's my ratio. The ratio, instead of being, a rotation ratio, is saying, here's how much travel I expect to see for every rotation, right? So as I mentioned before, we have one rotational degree of freedom, one linear degree of freedom. Now you'll find rack pinion in the toolbar, right about here in your toolbar. A left click, and then again, very much like the gear relation, you select the two mates that are involved. I have a slider mate here. That's my linear degree of freedom. And I have a revolute mate that attaches the handle to the arbor press. That's my rotational degree of freedom, right? Now I define a distance per revolution. So for every one rotation of the handle, how much up, down, how much linear movement do I expect to see out of this? And I can just say 2.25, for instance. Now, one big tip that I have is it's somewhat of a 50-50 chance, so to speak, that it's going to be going the right way. So what I recommend is, grab it and drag it and see. You can see this is not spinning the direction I'd expect, right, for an up-down movement. It'd be the opposite of this. So a tip in any of these gear relation, or any of these relations, I should say, there's an option for reverse direction, right? So I check reverse direction, and if at first it's going the wrong way, just reverse the direction, right? And one common question I get is, doesn't matter whether you grab one part or the other. This is free to move and so is this. Does it matter if I grab this one or this one? The answer is no. You can grab either part, rotate it, or drag it up and down, and you'll get realistic motion from both parts, right? All right, so one other thing I wanted to mention, when we talk about animate, I mentioned before you can right-click any mate with movement and animate it. Well, by default, when you do this, it's going to automatically grab the limits of that mate. So you can notice in this example, if I hit play, it only travels so far, right? And then it stops. And it stops not because the animation is timed out, it stops because I actually have established start and end values in the mate. The big thing I want to stress is, when you're doing this kind of design work, if you establish a limit in your mate, it's automatically recognized when you go to animate it. So you don't have to do anything special to restrict that motion, right? So that's another tip. Again, it's going to stop. It's going to respect your limits in the mate when you go to animate that mate. Very useful when you want to animate the full range of motion, like in my arbor press example here. All right. I noticed the double cog gear had two different rotation rates. How do you set up gear relation to have two different ratios per revolute mate? I'm not sure I follow. If we're referring to three sets of gears, then we may be referring to two different mates. All we're doing here is defining a ratio of the first to the second. So I'm entering that ratio in. There's not two different values per one relationship. Question may be too fundamental, but do all mates require a whole or point coordinate system for initial mate from part to part? They do not require you to create anything, no. So when you go to create a mate, you mouse over your part, and you're going to see all these parts, these points, I should say, appear automatically. So you don't have to do anything in terms of creating them beforehand. You can, but you don't have to. So in short, try creating a mate, mouse over your parts. As you see all these points appear, just select a relevant point to what you're trying to do. I would say in the extreme cases, you would need to create what you're referring to as a point coordinate system. We refer to as a mate connector. In the most extreme cases, you may have to create one, but I would say 9 times out of 10, just mousing over while in the mate command, you'll find a point that works. All right, so this is an example of a rack pinion relation. Again, all we're doing is defining that ratio between a linear degree of freedom and a rotational degree of freedom, right? All right, so let's move on to the next example that I have for you, and that is linear actuation. And it could be, kind of any type of linear actuation. It doesn't necessarily have to be, a screw type relation, but I think that's a more common example. So, any kind of threaded rod or, Acme type, threads where you rotate apart and you get linear movement based on that rotation and something driven by the thread, that would be a great example of a screw relation, right? And essentially, you're just saying for every one rotation of this, I expect X amount of travel and linear travel based on the amount of rotation that I get. So very simple. Again, just defining linear travel per rotation. So you can think of that if you're literally using a pitch on a thread. What's the pitch of your thread? That would give you that value. But again, the key is one rotational degree of freedom, one linear degree of freedom. Now, the example I have of this is a simple machine vise, but think of any kind of example where, a thread is used to drive parts in and out, right? That might be an example where you'd want to use a screw relation. Now, I mentioned before you need a rotational degree of freedom and you need a linear degree of freedom. So in the example of a machine vise, I have this spindle, and the spindle threads into the base. So I'd expect, this has got to be free to rotate, of course. The spindle needs to rotate, but it also needs to move in and out for every rotation based on the thread. So what I can do is define a screw relation. Right now, I have a cylindrical mate, right? So it's free to spin. It's free to, rotate in any direction. So it's free to move and rotate. It's free to move in and out, but the two aren't tied together in any way. All I have is one cylindrical mate. So here you can see the cylindrical mate. That cylindrical mate allows it to rotate, allows it to move in and out, which is what I want for the spindle, right? It needs to be free to do both. What I really need, though, is a relationship that defines between the two, right? That says for every rotation here, I'd expect X amount of linear travel. Now, the examples I gave you in the past, I was defining relationships between two parts. But in this example, it's just one cylindrical mate. That one cylindrical mate has the rotational degree of freedom, it has the linear degree of freedom, and that one mate is all I really need, right? So we'll choose screw relation from the toolbar. I'll select the cylindrical mate. Again, just driving home every one of these every one of these relations that I've created so far required you had, certain degrees of freedom. So in this case, the cylindrical mate. And then I just define what's my distance per revolution, right? So I'm saying for every one revolution of the handle, I want a 1/2 inch of travel. Now, I like to test it, of course, make sure that it's going the right way, and it looks like it is not, right? At least for a normal right-handed thread. So let's reverse it. And there we go. All right, so now I'm getting that rotation of the handle for every, certain distance I travel. And of course, as I mentioned before, I can also grab the handle and spin it, and I will get that same realistic in and out behavior. But again, all we did was define that ratio between those 2 degrees of freedom in that cylindrical mate. Right? Again, that is the screw relation. All right, so we've discussed a lot of the common kind of mechanical movements that you want, and relations are the kind of key way that you can create that type of movement, whether it be gear relations, rack pinion relations, whatever the movement might be. Those are simple ways to get started in those types of movement, but that's not the only way that you can create more complex motion. So I want to get into some of the other types of movements that we commonly get asked questions about. And the first, and probably one of the most common, is what about a cam? How do I create a cam type movement where, I rotate apart and I get linear actuation and so on? And the answer is tangent mate, right? So, and the neat thing about tangent mate is it doesn't just apply to cams. It also applies to any kind of scenario where you wanted to follow a path, for example. And I'll give you a few simple examples of this in just a bit, but this is a very much a robust tool in a few different scenarios. Cam is a useful example. Think of any kind of scenario where you want a part to follow a path, not just a linear movement or an up and down rotation, but it needs to follow a specific path of a part. This is another example where a tangent mate is really useful. So tangent mate has a lot of very good uses. Cam is probably one of the more common questions that we get. Now, what's really different about tangent mate versus all the other mates that I've shown you is you're not using mate connectors. You're using I'm defining a tangent mate between a series of faces or just a simple face, and so it's different in the sense that you're not clicking on mate connection points and saying bring these things together. I'm clicking on faces, a little bit more like old school methods. But cam is really the only scenario. Tangent mate is really the only scenario where I can see that being valuable, because really what you're saying is bring these faces together. Now, one question that's been asked, I can see it here and I get it asked often, is does Onshape provide video files of the animation? No. You would need to get a screen recording software and just record the screen for that. But there's no way to export the animations that you create in Onshape, other than, of course, just recording the screen. All right, so a cam type scenario is, of course, what we'd use for a tangent mate. That's what we need. So if you're looking for a cam actuation, definitely check out the tangent mate. Now, there are a few examples that I have, so bear with me here. I have an example of just a simple cam, and then we have something a little bit more elaborate in our cylinder head. But really just the same thing. All we're really doing here is defining, I want these two faces or these series of faces to remain in constant contact with each other. So let me edit real quick. What you'll see is essentially you have two selections, your cam and your follower, right? And in this case, I've just clicked on an edge, or a face, excuse me, but you'll see it automatically grabs all the tangent connected faces. So you don't have to go through and select every face of your cam. Just select one face and anything tangent to it will automatically be grabbed. And if I click on the second selection, again, it's just a simple face on the follower. So again, all we're doing here is saying bring these faces together and keep them together, right? And if we do, a simple animate, that will, of course, give us that kind of realistic up-down linear follower movement, right, that we get from a cam. So this is at its simplest level what a tangent mate does. It just brings a series of faces together and ensures they stay in contact in any kind of movement that you may have. So very simple cam example is one of the more common. Now, another example would be something like a series of cams, right? And this is nothing different besides the fact that you just have a series of tangent mates of cam to follower. We do a quick animate here. I believe this is our rotation for the cam. And what you'll get is that realistic travel, but of course, for 8 cams as opposed to 1. So my point in this being, it's just, one more level if you're trying to get that realistic camshaft movement in a cylinder head, for example. So that is a simple example of a tangent mate. And again, you're just telling a series of faces stay in contact with another face or series of faces. Now, this is useful in cam scenarios, but it's also useful in another very common scenario, and it's commonly referred to as paths or path mates, or, in general, I just want a part to follow a path, not a linear direction, not something I can easily do with other mates. Tangent mate may be useful. And, the common example I get asked is it possible to have a part follow a path in Onshape? And the answer is yes, you would use a tangent mate. Now, you can mate just the same way you would mate two faces of a cam and a cam follower. You would mate your faces of your path to the part you want to follow in that path. So again, it's the same tangent mate, same combination of things. Just select the faces you want to stay tangent, and it does not require mate connectors. So again, tangent mate, if you use faces, does not require mate connectors. It's one of the only mates that is that way. Now, you can use other things. You can use edges and so on. It's not requiring faces, but it's different in that you're not defining mate connection points. So following a path, we have a few simple examples of it. To start really basic, if I just had a pin that I wanted to follow in a groove, I can do that with a tangent mate. Right? So if we go into our tangent mate here, all it is a face on the pin and one of the faces in the groove. Again, remember, it automatically grabs everything that's tangent and connected to it. So I don't have to go through and select every one of these faces of the groove. I just select one and it grabs everything. But that's really it. I'm saying, I want this round face tangent to this face, and it maintains that relationship. So it cannot move past the edges of the groove, and it maintains, that path throughout. So that's a really simple example of path mate, part following a path. Now, when we get into, even more complex examples, you can get into some really neat stuff. So, one example of this is the fishing reel model. And the fishing reel model, if you think of any kind of standard fishing reel, you rotate it and the actual spool goes up and down as it spools line onto the fishing reel. And that linear movement, it's always been kind of a mystery. How do you get it to move up and down in a relationship relative to your rotation? And the example of this that I would give is this fishing reel. What's really unique about it, if we start to hide some of these shell pieces here, what's really unique about this design is that it allows you to put, similar to a path type relationship, one of these gears inside of a part, right? And when you rotate, let's go down and rotate, you'll get that up-down movement, right? Now, the key to the up-down movement is just simply that tangent mate. The tangent mate maintains that relationship. So as I rotate this, you can see the spool traveling up and down, and that up and down movement is caused by this part being locked into one of the gears with a tangent mate. So it's maintaining that tangent relationship throughout. Now, it is just another example of a tangent mate, but keep in mind, it's really, again, just using, let's hide a part here. It's really just using this groove and a pin, a boss sticking out of the gear that locates in this groove. And that up-down channel that you see is what gives us that linear movement, the up-down movement of the spool. So it's a very simple example, but I think a neat example of a tangent mate. This is another example where you really want, some part following a path. The path in this example just happens to be this channel. And that channel and the rotation of the reel is what gives us that up-down movement of the spool. So just taking it to one more level, of course, but the big thing to keep in mind is it's just another example where, I want a face in constant contact with another series of faces, tangent mate. All right, so let's move on. Now, the next example that I wanted to give is my last one. That is a swivel. And it's another commonly asked question. How would I go about creating a swivel-like motion in my design? And the answer is a ball mate. And you can think of any kind of scenario. The example I often give is like you think of control arms and a spindle on a car. The front end of a car has these control arms that pivot, and the spindle needs to pivot in other directions as well, in multiple directions, right? It needs to pivot up and down and left and right, and that's where you would need a ball mate to accomplish it, right? So I need that pivoting in multiple directions. No linear movement, right? It's not free to move in any direction. It's just free to pivot or rotate in any direction that's needed. Now, a front end of a car is a good example of a ball mate where you mount the spindle and it has to pivot in multiple directions to steer and bump and so on. But another example would be, like a pneumatic cylinder with a pivot eye, where you may have, linear movement, but it may be in multiple different directions. So let me give you, bear with me here, an example of this. Real simple example of just a pneumatic cylinder or a hydraulic cylinder, but on the end of the cylinder is a pivoting swivel eye. Very common type of thing where you may not have a perfectly lined up type of movement, and you want that rotational degree of freedom. So a swivel and an eye, very common example of a ball mate where the swivel needs to be free to rotate in all directions, but can't move in or out, up, down, no linear travel, right? So real simple ball mate, right? I can define center point on the swivel, a center point on the eye for the swivel, right? Just defining my two mate connectors here. One thing I would stress if you're new to Onshape assemblies, we only solve for the active mate while you're in the mate command. So you can see here I have the swivel parts that are still floating out here in space. If you want to see the end result, what it will look like finished, you can click solve. But by default, we're only solving for that active mate that you're in until you either click solve or you just hit the green check to accept. When you hit the green check, it will, of course, do that as well. But now I have that swivel motion, right? It's free to move up and down, of course, cylinder should, but also the swivel on the end is free to pivot in any direction, and that's where you'd use that ball main. So that is a simple example of a swivel. A front suspension on a car would be another example where you have control arms and spindles and things like that need to pivot in multiple directions but not move in any linear direction. And that's another commonly asked question. How do you go about creating that swivel type motion? All right, so that is what I had planned for you. Jumping back to my slide deck here, I am going to stick around and answer any questions that you have. So feel free to ask any questions in the Go-To Webinar Control Panel. There's a section there for questions. Please ask any questions that you'd like. I'll do my best to stop and address the questions before we end things here. But that's what I had planned. I want to say thank you, everyone. Feel free to ask any questions you'd like, but that's what I had. Thank you, and have a good day.